Okay, good morning, everyone. Let's start with our exercise class, second to the last exercise class. Um, so in this exercise class, I'll just look at the problem in the exercise sheets for this week. Yeah, there is only one problem essentially, and it is about the erasure protocol of a qubit with a battery. So first, let us kind of briefly outline the setting and yeah, see what we can do with this setting. So essentially, we're in this protocol, we're looking at three systems. So the first system is something that we call a battery. We label it as B, and the corresponding Hilbert space we label as HB. And physically is just a system which consists of infinite number of equidistant levels, energy levels. So it's this system B here. So has an infinite number of equidistant energy levels. Of course, this is physically an idealization because in reality you would not have an infinite number of energy levels which are equidistant. So realistically, we would need to bound this system with some energy value, but here it doesn't matter. And actually, we will see that for this particular protocol, we will only need a finite number of energy levels of this battery. The Hamiltonian of this battery, HB, is just a sum over essentially individual energies of each level. So it's like the 0th level has the energy 0, the level E1 has the energy delta, then the second level E2 has an energy 2 delta, and so on. Okay, so this was the first system. The next system is just a qubit, which we call S, a qubit S with the Hamiltonian HS. And sorry, with the Hilbert space HS, and a Hamiltonian, we put it as 0. So essentially we just say that there is a 2-level system and the energies of both levels are the same. So there is this degeneracy in energy. And this is exactly the qubit that we're going to try to erase. And the third system is a heat bath. So the corresponding Hilbert space we will call H heat bath. And the heat bath, we'll model the heat bath as consisting of n qubits, and these qubits will be different in a sense that each qubit will have a different energy gap. So we can write this out as is just a tensor. So the Hilbert space of the heat bath is just a tensor product of individual Hilbert spaces of each qubit from 1 to n. And then the Hamiltonian of the heat bath would be just the sum of the individual Hamiltonians of each qubit, so they would be non-interacting. So it would be n non-interacting qubits with linearly increasing energy gaps. So what do I mean by this? It means that the first qubit has the energy gap delta, the second qubit has the energy gap 2 delta, and so on. So maybe I can can copy this from here. Yeah, so here we have the heat bath. And then we have like the first qubit in a heat bath, the second qubit in a heat bath, the third qubit in a heat bath, and the nth qubit in a heat bath, and so on, with the linearly increasing energy gaps. Okay, so then what we can write, first we write the global Hamiltonian, which is just the sum of these local Hamiltonians. And we assume that kind of energetically, these three systems are not coupled. So just the Hamiltonian of the battery, Hamiltonian of the system, and Hamiltonian of the heat bath. The Hamiltonian of the system is 0, so it's just the sum of the Hamiltonian of the battery and the heat bath. Okay, and what we want to do essentially with these three systems is to conduct the following process, which I'll now describe in words, but then we will write it down mathematically. So essentially, we would have a qubit S, which would start in a maximally mixed state. So which means that this qubit is prepared in a state 0 with probability 1/2, or prepared in a state 1 with probability 1/2. This just corresponds to the density matrix of the state being 1/2 of the identity matrix. What we want to do with this qubit is we want to erase it. Namely, we want to put it in a state 0. And also we want to see kind of what is the energy that one needs to spend on this, and what is the exact process that we have to undergo. And we also have these two other systems, which are this heat bath, which is just a collection of the qubits with the increasing energy gaps. And we also have a battery. And the idea is that all the qubits in a heat bath start in thermal states. And the battery starts in a pure state, let's say in the state corresponding to the 0 energy. And then the coupling process happens so that the state of the qubit and the state of the battery are raised if the state of the qubit in a heat bath is in 1, and the opposite happens if the qubit state is in a state 1 and and the energy is in some upward state. Then they both go down if the qubit of the heat bath is in a 0 state. So essentially, what happens is that we kind of take the energy from the heat bath and kind of transmit it to the battery. While in the process, also manipulating the state of the qubit S, and the other way around, because it's a unitary process. We have to have this both processes of going up and going down captured in it. And then why do we have so many qubits in a heat bath? Well, it's because we just repeat the same process again and again and times, but each time we use a different thermal qubit. And since they all have different energy gaps, their thermal states, which depend on the energy gaps, would be different. And in the end, that would allow us to raise the state of the qubit S to the state 0, 0 in the limit of the number of this qubits in a heat bath going to infinity. we'll also look at how the what will be the energy distribution for the energies in a battery in this process, which will look a bit like a random walk. I mean, not a bit, it will be exactly a probabilistic random walk, and one can model it like in Mathematica or Python or wherever you like. And yeah, so then we can look at this energy distribution in the battery. Okay, so now let us proceed. So what we are doing, we are applying the unitary process. We're applying actually conceptually the same unitary n times, but just coupling to the different qubits of the heat bath. So we can just write it as applying the unitaries. So first U1, U2, so on, and UN. And each unitary, as I said, it does the following. So for example, if the qubit S is in 0, so suppose that we are looking at how the Lth unitary is applied, then suppose that the qubit S is in 0, yeah, the battery is somewhere here, the state of the battery is somewhere here, and then we're looking at the Lth qubit of the heat bath. And then what happens is, so first the 0, so the following operation happens. So the 0 state of the qubit goes to 1, the state of the battery goes up L delta, and the state of the heat, and the state 1 of the heat qubit, heat bath qubit goes down to the state 0, so down L delta. So kind of these, so we have the energy conservation. And the reverse process, which is captured also by this unitary, has to be that if the qubit starts in, a qubit S starts in a state 1, then it goes down to 0. The energy, if it starts somewhere here, it goes down delta L, and the state of the heat bath qubit goes up from 0 to 1, where these 0 and 1 are again separated by L delta. How do we write this unitary process analytically? Well, it's a bit lengthy. That's why I changed the orientation of the sheet. So UL would be, so we have to sum over all levels of the, yeah, we have to sum over all levels of the battery. Yeah, I wrote that down. So we sum, and what we get is, so the first action would be going from, this is L, K, 0, 1. So the first action is going from the position as if the state was, the state of the qubit would be 0, the state of the heat qubit would be 1, and the state of the battery would be EK. Then what happens is we can kind of transfer the energy of the heat qubit to the battery, also reversing the state of the, flipping the state of the qubit S in a process. So this is the heat bath, which goes to 0, the qubit goes to 1, and the energy of the battery is raised. Also, the reverse of this process, of course, happens, which does exactly the opposite. So given that the state of the qubit is in 1, so So the state of the qubit is in 1. The state of the heat bath is in 0. And the battery is in some state which we label as EK plus L. It doesn't really matter because, yeah, we sum over all Ks anyway. And what happens is we kind of, so the heat bath takes away the energy from the battery. So the heat bath energy is raised, the qubit's state is flipped in a process, and the energy of the battery is lowered. Okay, so this is kind of the process that we wanted to capture with this unitary. Also, we have to, of course, say that on the rest of the systems, we just apply the identity. But by itself, to write the unitary as just like this is not sufficient, because, I mean, the unitary has to be this matrix transformation, which would give us U dagger equals identity. So the rest is just us completing this process. So this process would be described as a unitary. And this can be done by just adding this term. So just as an exercise, you can actually prove that it is a unitary by just looking at the U dagger, which actually would be the same as U, and then multiply U by U dagger. Okay, so let us now proceed with the analysis of this unitary, or of composition of n such unitaries. So the first, there is a question. Okay, so yes, exactly. Okay, you figured it out. So so the identity is applied to the rest of the system exactly because the heat bath consists of n qubits, and in each step of the process we only use one of these qubits. So the rest of the system is just the rest of these qubits, which don't matter for a particular step, but in the end, all of the qubits are used for like in general when we do all the n steps. Okay, so the first thing that we need to kind of make sure is that we are working, that this unitary still allows us to work with these three systems as in them being isolated systems, in the sense that we need to make sure that this unitary preserves the energy that that is in the system, in all these three systems combined. Of course, this kind of intuitively follows from the way we constructed the unitary, because we made sure that the energy from the heat bath is transferred to the energy of the battery in the same extent. So if we take delta L energy from the heat bath, then the energy of the battery is raised from E to E, from EK to EK plus L. So exactly L levels up. And the other way around. To kind of to convince ourselves of this, like we just need to show that the unitary U, the composite unitary U, commutes with the global Hamiltonian of the system. So we want to show that global energy is conserved. So we need to show that H global commute with U. So maybe we say here conserved after applying U, which is just the composite of these unitaries. To show this, it is actually sufficient to show that during each step of the protocol, so during after applying each of these individual unitaries from U1 to UN, energy is conserved. So that H global U1, sorry, UL, commute. And then, of course, if we just applied all these operations in a sequence, all these ULs, the composite operation will also not change the global energy. Okay, so let us remind ourselves what is H global. So H global is just the Hamiltonian of the bath plus Hamiltonian of the battery plus Hamiltonian of the heat bath plus the Hamiltonian of the qubit S. The Hamiltonian of the qubit S is 0. The Hamiltonian of the battery is just the sum from, let's not call it K, from J minus infinity to plus infinity, J delta, EJ, EJ. And the Hamiltonian of the heat bath is, what was it? Sum over, say, J from 1 to N, delta J, was it delta J 1 J rest. Yes. Okay. So now let us see what is H global by UL. So what we have here, this is gonna be a bit painful, but we know the answer that they have to commute. So let's just look in that future, hopefully. Maybe J here wasn't the best solution. So let us rename it as, let's say M. Have here from M equal 1 to N, delta M, 1 M, the rest. And this we have to multiply by this monster, which is already on the top of the page. So we have the sum. So I'll rewrite this here as the tensor product of the individual states on each system. So this would give me AK plus L AK on B tensor product. Yeah, and actually here, since we write the rest here, in principle, I should also write here the rest, because these are just the states on the battery. Okay, so here we have EKL, EKB, then 1, 0, S, then 0, 1, L, plus ek plus L, 0, 1s, 1, 0, L, the rest, plus battery, 0, 0, S, 0, 0, L, plus 1, 1, S, 1, 1, L. Okay, now let us look, before we open the brackets and continue, let us just analyze in principle what we're getting here. So in the end, if we just open this bracket straightforwardly, we'll just get a sum of 6 terms, because we have 2 terms in the first brackets and 3 terms in the second bracket. Sorry, 3 terms, 4 terms. Apparently I cannot count. So we get 8 terms. And let us just see which terms survive and in which way they survive. So first, let us look what happens if we take this term together with this term. So what happens here? So here we would conjugate this EJ here. We'll multiply this EJ here with EK plus L here, which would give us 0 in all cases except for when J equals K plus L. So there is that. So the first term in the sum, we can just write it as sum from K minus infinity to plus infinity. So J equals K plus L. It would be delta. Here we have EK plus L EK on B. Then all the other comes from the second term, because on the first term we just have the identity. Plus. Okay, now let us look at the second term. So now what we're trying to do, we're going to multiply this EJ here with the EK here. So this term will only survive if J equals K. So here we would get sum from K minus infinity to K plus infinity. K delta EK plus L on battery. All the other stays the same. Yes, and here also maybe just take it as a convention, since I'm not doing it explicitly. So here we just assume that in the sum we're just writing the terms where the corresponding matrix is not identity. So ideally I would need to write here also identity on the rest, but let us just say that this kind of implicitly happens, and I don't write it down this way. Okay, so this gets a bit uncomfortable, so what I suggest we do, we copy this thing and go to the next page. Okay, so these were the terms. Then we continue with the next. So let us take the same term here. And now look what happens when we multiply it by this term. Well, nothing happens. Both of them are preserved in a way they are. So I'll just promptly change j summation over j to summation over k. K delta ek ek. Here we have this 0, 0 s plus, I'm sorry, 0, 0 l plus 1, 1 s, 1, 1 l. And there is like the identity on the rest. Okay, these were all the terms from the first term in the first bracket. Then let us take the second term. So the second term is this Hamiltonian of these heat bath qubits. Okay, so what we do now is we take the second term and we see what is this 1m multiplied by. So this is summation over m, right? So we have to multiply this 1m by 0 acting on the lth qubit. And in all other cases, except for when m equals l, we would actually get a result. We would actually just have no action on the Hamiltonian on that term in the sum corresponding to that particular heat qubit in a bath. We would have no action. But for the lth qubit and that sum, we would actually nullify kind of the contribution of that qubit. So essentially what we would get is, so we keep the sum. So we still have the summation. One zero s. And here we would have sum over m from 1 to n, delta m, 1, 1 m. And then there is also the rest, identity on the rest. For all cases, but except for the case when m is not equal to l. So one can say that this is just the sum over these minus delta L 1 1 L. Okay. Then what happens in the next term? So the next term is us multiplying this 1m here with the corresponding 1 here. And again, for all cases, except for when m equals L, we're multiplying not exactly by this 1 0, but we're multiplying by identity, because this 1 0 only acts on the lth qubit. So then what we would get is we keep the EKs part, so the battery part, the qubit part. Then we almost keep the heat bath part, except so maybe it's good to write here the rest. Here also the rest. So we almost keep this part, except we take away the part for the Lth qubit. And because we know how it acts on the Lth qubit, it just turns this 1 1 to 1 0. So we would have here is plus delta L 1 0 on L. Okay, and the last part is multiplying the second term in the first bracket by the term here. What we're getting here is, so the S part, we don't really care. And the battery part, we also don't care. Now we need to conjugate, we need to multiply 1 here with a 0 here. And this happens only for the Lth qubit. In all other cases, the rest of the terms survive. So we end up with what we already looked at. So it would be just the sum minus the contribution of the Lth qubit. And the second term would be just, so the battery 1 1 on system S, and then we're multiplying this 1 by the 1 here. And what we're getting is essentially, even for the qubit number L, we get from 1 1 to 1 1. So essentially nothing changes in the sum. Okay, so then what one needs to do is to repeat the same thing for U L multiplying H global, and derive in a similar way. And one will see that these two things are actually the same. So I'm not doing it here because the process for the UL H global is essentially the same. To actually equate them, you may need to open some brackets which are here in the sum, like for example here and here, and then just compare each term to each other. Maybe you will need to change the summation. Like for example, if you have this EKL EK here, maybe you need to shift by L or so. But since it's a summation over all k's from minus infinity to plus infinity, it doesn't really make a difference. And also, maybe you need to open this bracket here. So this is just an exercise to make sure that indeed the energy is conserved. Though intuitively and by the construction of our unitary, we actually see that the energy has to be conserved. So usually usually we don't actually check these things. We just make sure while constructing the unitary that the energy is decreased in one system and increased in the other system in the same manner. And also, like, this is not like the problems in the exam would look like. So this is just an exercise which is good to do once and never think about it again, and just after that take this thing, look at these things more intuitively. Okay, so what shall we do next? So the next is we're trying to apply essentially the unitary to a particular initial state. And the initial state will take as follows. So the initial state will be the state of the battery will start in a pure state corresponding to the zero energy, which we label as E0. The state of the qubit, as I said, would be maximally mixed. So it would be 1/2 identity. And the states of the thermal bath qubits, of the heat bath qubits, they will be in thermal states. And we already discussed these thermal states in a previous exercise class. So essentially this would be just tensor product over all states of the qubits of the heat bath. And each individual state will be just 1 over ZL of T 0, 0, L plus e to the power minus L delta over T 1, 1, L, where ZL of T is just this 1 plus e to the power minus L delta over T. It's just a normalization factor for this probability distribution. Okay, so this we already saw. Just as a note, here I take the Boltzmann constant. So usually we have the kind of the thermal state. In the thermal state, we have exponential e to the power minus energy gap over k Boltzmann T. Here I just take k Boltzmann equaling 1. So I can just absorb that constant into our definition of temperature, and that is fine. Okay, and then we want to apply our unitary UL, which I'll rewrite here because we might need how it looks like. And the first step while I'm writing, so the first step that we will do is we will carry out the first unitary on our initial state. And then we'll notice which patterns we see there, and we'll try to then kind of make the question about the energy distribution or the state of the qubit less complicated than if we would directly had to apply all these n unitaries to the state. Like, let's not think about how the final state looks like at all. Like, I think it gives you a headache. At least it gave me a headache. So so we'll just decompose this problem into a simpler problem that can be easily modeled. Now I'm just rewriting this elf unitary. Okay, so let us apply U1 to rho 0 and see what is the joint state of all these three systems. So of the battery, qubit S, and the heat bath after the application of the first unitary. Great. So rho 1 would be U1, rho 0, U1 dagger. Yes. So what is this equal to? Okay, this might be a bit painful, but let us try to carry this out. So let us first write how we can write the first unitary U1 acting on the state rho 0. So as you see in the definition for the unitary UL, we have the summation over energy levels from minus infinity to plus infinity. This summation makes it sure that kind of the energy change in the battery is applied to every level that is in the density matrix description of this battery at the particular step of the protocol. Do we actually need this for the first step of the protocol? We don't, because initially the battery starts in a state 0, and the only states and since the energy gap of the first heat bath qubit is exactly delta, actually the only two states the battery can go to from the state 0 are either 1 or -1. So actually in our sum over the states E0 or over the states EK, we actually only need the state E-1, and so E-1, 0, and 1, and that's it. So one can also see this. Maybe I already give this kind of geometrical random walkish explanation of this here as follows. So if we're looking only at the states, so this I will continue a bit later. So let us for a moment forget about the fact that the heat bath exists. Suppose that we are only looking at the states of the battery and this qubit S. So one can see this as so this analogy I find useful while constructing the solution. Maybe you will too. So one can see the initial state of the battery and the system as being a state on this kind of two-dimensional plane, where the vertical axis corresponds to different energy levels of the battery, and the horizontal axis has only two coordinates, 0 and 1, which correspond to the state of the qubit the particular energy state of the battery is correlated with. So in this case, since we start in a state in a joint state of the battery in the system, which is essentially 0, 0 on battery by 1/2 0, 0 on S plus 1/2 1, 1 on S. And as you remember, when we have such a mixed state, it just corresponds to the quantum mechanical description of a certain probability distribution on the states. And this description just means that we either start with 1/2 probability in the state E0, 0. So E0 state of the battery, E0 state of the qubit, or in the state E0, 1. So if I, for example, mark this as 0 and this is 1, then we start here and here with the equal probability. Then what happens during each step of the protocol? So we will see this mathematically when we apply the first unitary, but let us think about it more intuitively. So the idea of the unitary that we apply is that there are two possibilities. If the state of the qubit S is in the state 0, then it can always happen during the round that with some probability, which is governed by the heat bath that we're using. The state of the qubit can flip to 1, and then subsequently the state of the battery will, the energy of the battery will also go up. So what can happen essentially is this kind of movement. So 0, the state of the qubit. So this can be labeled by S, and this is the battery. So the state of the qubit goes from 0 to 1, and the energy of the battery is raised. What can also happen is that if the state of the qubit is in a state 1, if the qubit is in a state 1, then because the heat bath is always, which we use, is always with some probability in a state 0, then what can happen is that the state of the qubit S is flipped from 1 to 0, and subsequently the energy of the battery is lowered. So this movement happens. And this step corresponds to the first step of the protocol. Or there is actually an additional option, which is with some probability nothing happens, and the system stays in a state E00 or in a state E01. So essentially, we can portray this as this particular, as a certain diagram. So we have the system in the state E00 with probability 1/2, and E01 with probability 1/2. Then what happens during the first step? So during the first step, if we're looking at the state E00, then this state can either go to E11, or it can stay in E00 with some probability, which we can derive directly when we start doing this thing analytically. Or if the system is in state E01, then it can go to E-1, 0, or it can stay in E01. Then one can already start to see this thing as like this constrained probabilistic random walk, where at each step the system goes with a particular probability to the next or previous energy levels, and with some probability can stay put at the particular place. This random walk is a bit funny because it also says that every time we make a transformation, we move the energy levels, the step in our energy levels that we conduct is increasing linearly. So for example, this was the first step, right? So what can happen during the second step? So during the second step, let me change the color. So this E-1, 0, from here we can go up to E1, 0, because during the second step we can move only two slots up, 2 energy levels up, because we use the next heat bath qubit, which has the energy gap 2 delta. We can go up from here. We can also go up from E0, 0, because during the previous step, the system stayed in that state, the battery in the system stayed in that state with some probability. From E0, 1, we can go down to E minus 2, 0. Yes, and also we can go from this E1, 1 back to E minus 1, 0. So these are essentially the steps that we can make during the second application, and so on and so on, and yeah, in the end, up to n steps, you would get some probability distribution. Also, another way this walk is funny is also because the probabilities of these transitions, because they also depend on the energy gap that the heat bath qubit has that we use during that step. These probabilities also change, and not linearly, since the energy gap is in the exponential in the heat bath qubit. Okay, so this was the idea of how to model this as a random walk. Now let us see what are the probabilities of the steps that we make in this random walk and why this works. So for this, we still need to apply our U1 to the initial state rho 0 and try to recover the pattern that I just told you about. Okay, so again, which state are we applying our unitary to? So it will be E0, 0. Then this is 1/2 0, 0 s plus 1, 1 s. Tensor product. So for the first application, we only need to consider the first qubit of the heat bath. Z1 0, 0, 1, so the first qubit, plus e to the power minus delta over t, 1, 1. And here we have U1 dagger. So U1 is equal to U1 dagger. So that is easily, you can easily see that if you conjugate the UL for any L, you actually would get it back. So that is very handy for us. So maybe I note it here. Another thing that is very handy is that the initial state is symmetric. Like it's symmetric in this bracket sense. So we don't have any states here as in 0, 1 or 1, 0, which would kind of create some certain asymmetry in a way the unitary is applied on the left and on the right. Here it's symmetric, which means that actually we can just look at how the unitary U1 is applied kind of to ket on the left side, and then the unitary U1 applied on the right side would be just symmetrically applied. So this is kind of a maybe a bit of a trick how to handle these applications. Okay, so now let us see what exactly happens here. So first we want to look at how the unitary is applied, how the transformation is applied to the following. E0 is 0, 0, 0, 0, 0. So we have E0 on the battery, 0 on qubit S, and 0 on the heat bath qubit. In this case, the transformation does not happen because there is no energy to be transferred. Because actually the qubit is in the state S, so the qubit S is in the state 0, then it kind of requires some energy to be transferred. But the heat bath is in the state 0, so there is no energy to be transferred. So essentially, this state stays the same. So it would be 1/2 Z1, which are just the coefficients that I take out. E0 is 0, 0, 0 S, 0, 0 on the first qubit of the heat bath. Fine. Now let us consider E0, qubit in a state 0, and heat bath in a state 1. This is exactly when transition happens. So then this state is, which is with the coefficient e to the power minus delta over t over 2z1. This state is transformed into E1, E1, 1, 1 on S, and the state of the heat bath is lowered, 0, 0 on 1. Okay. Then the next combination we consider is the following. State of the battery is 0. State of the qubit 1. State of the heat bath 0. This is also a state when something happens. So here we can lower the energy of the battery and raise the energy of the heat bath, and also flip the qubit from 1 to 0. So here the coefficient is 1/2 Z1 of E minus 1, E minus 1. Then we flip the state of the qubit from 1 to 0. And finally, we raise the state of the qubit of the heat bath. Okay, and the last term in the sum to consider is the following. State of the battery E0, state of the qubit 1, and state of the heat bath qubit 1. Nothing happens because the qubit S, being in a state 1, would actually want to be lowered together with the battery. But for this, the state of the heat bath would have to be in a state 0. So the heat bath already has the energy. Nothing to transfer, so this state stays the same. And the coefficient here is 1 minus delta over t, 2z1, E0, E0, 1, 1 on S, 1, 1 on the first qubit of the heat bath. And then there is also the rest. Okay, so this is the state of these three systems after applying the first unitary. Now let us look, and then again, what you can see here is that because we started with this mixed state, which is essentially in the for these three systems in a diagonal can be expressed as a diagonal density matrix. Then, like after each application of the unitary, of the corresponding unitary, what we would also get, we continue to get, is the same diagonal state on these three systems. So this kind of tells us that we can continue to look at these kind of energy distributions as a quantum mechanical description of some classical distribution. Just let's say it's some again, how do we interpret mixed states? As that we have some classical distribution, and then we prepare the quantum states corresponding to this classical distribution. So that's why we are still able to think about this process, especially on the energy, as a random walk. So to understand this further, let us look at the reduced state of the battery and the system qubit S after after application of this first unitary. So what are we left with here if we take the reduced state of the battery in the system? So from the first term, we're just left with this. The second term gives us this. Third term so this is very easy. It is very easy to take the reduced trace, so to take the partial trace of such a sum, because here we just have all three systems. So the state of the system, the state of these three systems expressed as the sum of these states which are separable for each system. And so there is no entanglement per se. And then taking the partial trace becomes extremely easy, as you just kind of wipe out the third system at each term of the sum, especially that this third system is always in this diagonal state. And then you get the reduced state. Okay, and here we can group out some, so let's here again look at what we've got. So we started in the states of battery and system, as I labeled them E0, 0 and E0, 1. And these are both with probability 1/2. As in, again, remember this picture with this kind of randomish walk. Yeah, I can even redraw this here. So E0, 0, 1, 1, E-1. So we started here and here with equal probability. Then let us look at the terms in this sum for the reduced matrix of systems B and S. So the first term corresponds to the system staying in the state E0, 0. This happens with probability 1/2Z1. The second state corresponds to the system going to the state 1/1, which is this state here. So this transition happened. This happened with a probability e to the power minus delta over t over 2Z1. E1, 1. Then for the next term corresponds to the system going to the state E-1, 0. So in our geometric picture, random walk picture, this corresponds to this move. This happens with the probability 1 over 2z, or 1 over 2z1. Yeah, by the probabilities, I'm just writing out the coefficients in front of the corresponding terms in the sum. And finally, the final term in the sum just corresponds to the system staying in the state E0, 1, which happens with probability e to the power minus delta over t over 2z1. So if we label P1 as e to the power minus delta over t over 2z1, then we can actually just substitute these here as this is 1 minus P1, P1, P1. Oh, sorry. This will be 1 minus P1, P1. And one can show that during each step of the protocol, this is exactly what happens. So whenever we start, so suppose that we have at some case step of the protocol, we have some distribution over the energies, or more like we have a distribution over over these nodes in our picture. So for each node, we would have a particular probability that the system ended up in that node. And then for each next step, we actually know what is the probability of the system being found in the nodes given the probability distribution at the previous step. And this allows us to kind of to model this this computationally. Yeah, I have tried to find the analytical solution for this, but yeah, I kind of failed, so I just used Mathematica in the end. And to keep in mind is that the energy gap, so the steps every time after application of every unitary increase, and also the probabilities, this P1s here, they also change because on the key step you would have pk e to the power minus k delta over t over 2zk, because they also depend on the energy gap of the thermal qubit that you use. So yeah, and maybe last thing to look at for this row 1 is the reduced state of the battery. So the reduced state of the battery of course it's useful to know in terms of calculating the energy of the battery, but you can already probably guess how to do it. So so again, we just take the partial trace of the rho bs to get the state rho b, and what we get here is just 1 over 2z1 0 0 plus, from the second term we get e to the power minus delta over t over 2z1 e1 e1 plus the third term gives us 1 over 2z1 e minus 1 e minus 1 plus the last just gives us this. The last term just gives us e to the power minus delta over t over 2z1 e1 e1. So e0 0. Okay, so we have some terms which are the same for the e0 e0. So here we get And we also know that Z1 is 1 plus e to the power minus delta over t, which means that we have 1/2 E0 plus this. So what does this mean? This means that after application of the first unitary, if we're only looking at the state of the battery, of the energy of the battery, the state of the battery with probability 1/2 stays the same, so it's 0. With probability e to the power minus delta over t over 2z, it goes up. With probability 1 over 2z1, it goes down, one step down. So one can notice here that the probability, so the probability of the system of the battery going one step down will be higher than, will be always higher than the probability to stay at the state 0 or to go up. And this is exactly because we use the bath qubits, the heat bath qubits, which are in the thermal state. Which means that, so for the battery to actually raise its energy, the heat bath qubit has to be in a state 1, so it has to be excited. However, for the heat bath qubits in the thermal states, the probability of them being in an excited state is much lower, especially when the temperature is low or the energy gap is too big. So this probability is always lower than to find a heat bath qubit in a ground state. And this is why the heat bath qubit is less prone to to induce this energy raise in the battery, but it's more prone to induce actually the lowering of the energy in the battery. And yeah, so this essentially happens. Then the reduced state of the qubit is, which we can also look at. So this is after the application of the first unitary. So let us see. So we have this rho BS here, right? And we take the partial trace over the system B, which means that we're just left with 0, 0s and 1, 1s on system S. And for 0, 0, we would have let me see. So for 0, 0, we would have 1 over Z1 plus, so 1 over 2Z1 plus 1 over 2Z1, which would give us 1 over Z1. 0, 0. Plus, of course, the remaining would be just by normalization would be e to the power minus delta over t, or Z1, 1, 1 on S. And as we remember, the aim of this protocol is to erase the qubit. And we see that we started with the state of the qubit, which is fully mixed. And after the first application, we came to this reduced state. One can show that after n applications of the unitary, the states of this qubit S would be just the thermal state of the corresponding heat qubit that we have paired it to. This can be shown by the following. So again, forget about the heat bath qubit. Suppose that you just have this random walk over this joint states of the battery and the qubit S. Then to calculate and suppose you have some energy distribution over these levels at some point. And the way to calculate the probability of sorry, I think the Zoom the Zoom quit unexpectedly. Yeah, we just have a bit left. So sorry for this unexpected interruption. So back to what I was saying. So suppose we applied some unitaries, we have some energy distribution over the states of En, let's say EI0, EI1. To calculate the reduced density matrix of the system S alone is just to find the probabilities with which the system can be found in 0 state and 1 state. And for this, you just need to sum over all probabilities of finding the system in the state EI0 for the 0 state and EI1 for the 1 state. And yeah, and this can be done by induction at each step of this random walk. So maybe and then at the end step we arrive to this state, and if n goes to infinity, then actually the second term does not matter, and we only and zn is close to 1, and then the row Sn, the state of the qubit, is approximately in 0. So the aim of the protocol is achieved. We started with the qubit in a mixed state, and then by this consistent coupling to the different heat bath qubits with different energy gaps, we erased it to the 0 state. Okay, so now a bit about the random walk, just to give it a more mathematical description. So maybe just let me copy this from the previous. So after the first step, we arrive to this. What happens after Keith's step? So suppose that after Keith's step, we arrive to some probability distribution over energies. So we have the energies ranging from E minus n0 to En, and the probabilities at Keith's step. So the probability, for example, to find the qubit in a state 0 at the energy minus n would be qk minus n0, qk 0, 0, and so on. And the same for the qubit in a state 1. So this is the probability of finding the qubits in a state 1 and the battery in a state E minus n, and so on. So the first argument corresponds to the energy level, the second argument corresponds to the state of the qubit S. And then at Keith's step, so at Keith plus 1 step, the following happens. So suppose that the system is in a state E minus I0 or in a state EI0. So if the system is in a state E minus I0, then the only way it can only increase the energy, or increase the energy of the battery, or it can stay. So it either stays or the energy of the battery is increased. so the energy of the battery is increased with the probability the heat bath state has some energy, which is pk plus 1. And this probability has to do only with the state of the qubit of the heat bath. And it stays the same with 1 minus pk plus 1. And the same for this state. So if the system is in a state EI1, then it can either only lower its energy or it can stay the same. And it can only lower at the k plus 1 step, it can only lower energy by k plus 1 levels. So that's why I minus k minus 1. And if it lowers the energy, it means that the heat, it does it with the probability with which the heat bath qubit is in the ground state, which is 1 minus pk plus 1. This is pk plus 1. Then one can actually write, based on this diagram, one can write the probabilities which correspond to qi minus I k plus 1 based on the previous step probabilities. So also here I use one particular observation, which really helps. So here, as I see, so here I made a bit of a leap going from this probabilities, which only depend on the particular state of the battery and the system, to going to just probabilities, which is a bit of a cheating, but let me explain. So again, we're looking at this process which we can mathematically describe as a random walk. And this process is very constrained, which lets us make some observations. So one can see that during each step, we can only make a move which has a positive tangent. So we can only move up and right, or we can move left and down. And given these two states that we start with, actually, we can never arrive in a state such that it would be on the left and up. Because if we go left, we always go down. And moreover, with each step we have to increase our steps. So which kind of leads us to the conclusion that actually all the states for which the qubit for which the qubit is in the state zero have negative energy. So they're all here. And all the states of the qubit, all the states of the battery for which the qubit, which are correlated with the qubit being in the state 1, are actually positive. Which means that some of these probabilities, namely the probabilities of the qubit being in a state 1 and being negative, and the battery having negative energy, are 0, and the states for the probabilities for the states which for which the qubit is in a state 0 and the energy of the battery is positive are also 0. So we are only looking essentially at these probabilities. Then we have a different probability for two different probabilities for the system having 0 energy and being in the state 0 or 1 qubit. And then we have the system, the system such as that the qubit is in state 1, but the battery has the positive energy. Okay, and using this this kind of mathematical model of the random walk, one can also model the model what happens with the energy distribution after application of n unitaries. And since I'm not sure if analytically this can be solved, but one can always model it as a random walk. And just as a couple of closing remarks. So I applied this process on the Mathematica. So for different parameters. So for example, the first the graph on the left corresponds to the number of unitaries applied, which is 30, and the parameter which connects the energy gap with the temperature, I took it as 0.1. And here we see that there is this funny peak on the right, which I'm not sure how to explain, but it's a funny random walk. But we see that the most of the peak is concentrated around some energy value. And what you can also see, you can also look at what is the average energy and what is the kind of the distribution. So the variance of the energy here. And the more and more unitaries we apply, so for example, the graph on the left is for 50 unitaries, kind of the more and more we see that the average energy value that we spend on this process is kind of becoming more and more like this sharp distribution like. Okay, so and here we also see that the remark I first made, that the battery system is always more prone to reducing the energy than going up with the energy, and these graphs show exactly this. And they also allow us to extrapolate the energy cost that we would need to erase the qubit in the limit of n going to infinity. So if we apply n, so we apply an infinite number of these unitaries, then this would correspond to the energy cost of erasing a qubit from a fully mixed state to a 0-0 state. Okay, I think this was a lot. Also, I have to say that again, this is just a problem which gives you an explicit protocol of how to erase the qubit. There's not going to be such protocols in the exam, so this is just for you to see how you can tackle this more advanced problems, and just to catch up on the techniques again, like how do we apply unitaries to density matrices, how do we take the partial trace and everything. How do we calculate the average energy for given density matrix, and so on. Yes, so I'll be posting the solutions hopefully on Monday or on Tuesday. I also know that I owe you the POVM decomposition, which I didn't have time to do because it's the end of semester and things are a bit more strained. I'll also post the mathematical code that I used to derive these distributions and to model this random walk. Yeah, don't expect it to be like very nice or very optimized because I haven't programmed in a very long time. So yeah, so if you have any questions about this, please ask them now. But I can imagine that you're very tired of me talking about this batteries and energy levels and everything. You can always send me a question by email or so. Okay. Okay, if there are no questions, then thank you very much. Yeah, have a nice end of the week. Bye. There is a question, will we have an exercise sheet next week? Yes, there will be an exercise sheet for the next week. Bye.